Hi, I'm Rob Stringer from High Point Access and Rescue. In this video we're going to cover anchor angles. We're going to look at the relationship between the angle and the loadings back onto the anchors. Okay, so what we've got is we've got a 100 kilogram mass down here. That 100 kilograms is connected through a series of connectors into an S-type load cell. So an S-type load cell there, which is connected with a wire back to an indicator. So on our indicator panel we read 100 kilograms. So that's just reading the mass down the bottom. Okay, so I'm going to lower this mass down. I'm going to put it onto two separate anchor points. So we're going to hoist the mass into place. So we've got a 100 kilogram load coming up through a focal point up to two separate anchors and a load cell on each anchor. So first things first, we need to estimate what this angle is. Now there's a few methods that people use to make that estimation. One is this method. So you hold two fingers up like that, and that's pretty much that angle inside there. So that's roughly 30 degrees, right? So that angle's 30 degrees. You can get iPhone apps and all sorts of things to try and measure that accurately, but down in this region it doesn't matter. There can be a bit of variance in there, and it's not going to change much up in there as loading, which I'm going to show you. 30 degrees. And you'll notice on this cell we got 52. On this cell we got 51, so it's pretty close to 50%. So we're going to put this on a chart. So as we go through, we're going to mark this on a chart. So degrees along the bottom. That degrees refers to this angle inside here. Yep. And up here on the y-axis we've got our percentage of load, so percentage of actual load there. So we've got a 100 kilogram mass, which makes this easy. Okay, so what we're saying is at 30 degrees, we've got 50% of the load on each anchor. So now we've got a 60 degree, or pretty close to a 60 degree angle. Again, there's a few methods of estimating that. One is this. So people put their hand up there like that and think, well, that's pretty close to 60 degrees there. Another method, what we've got, if we take this length from the focal point to the one anchor, and if it's the same distance across the top, and same distance down this side, we've got ourselves an equilateral triangle. So in an equilateral triangle, if all sides are equal, all angles must be equal, which means that this angle must be 60 degrees. Okay, 57 there, 57.5 there. Well, let's round that. We're going to round that to 60. So 60 degrees equals 60%. Nice and easy to remember. Okay, we've got a 90 degree internal angle there. A few methods of estimating that. One is this, so that angle between those, 90 degrees, pretty close to it. I can use a smartphone to do that. So if I place the smartphone there, I know the corner of a smartphone is 90 degrees. I could use a pad or a book or any object that's got right angle corners. Gives us 90 degrees. So it's pretty easy to estimate that one. So 90 degrees there. If we have a look on our load cell, on one side we've got 69.5. Over here we've got 69.5. So they're exactly the same, and they're roughly 70%. So estimate for the board here, at 90 degrees, we've got 70% of the load on each anchor. Now let's have a look at the chart there. We went from 30 degrees all the way up to 90 degrees. So there's a difference there of 60 degrees. And what that did was that changed our load from 50% up to 70%. So there was only a 20% change in load with a 60 degree change in angle. Now, I think that's quite significant. So we just bumped this up to 120 degrees. There's a few methods of working out 120 degrees, but accuracy diminishes the higher we get. One method is this, so people put their hands up there like that. They think, well, that's 120 degrees. That's not very accurate though. Okay. The other one is if you stand back and look at it, this angle here should equal that angle, which should also equal that angle. Again, that's difficult to do without some sort of protractor, but as a bit of an eyeball, you can see that angle equals that angle equals that angle. So if all angles are equal out of 3, there must be 120 degrees in it, in each angle. So let's put that up there, 120 degrees. Now if we look at the loading on that, if all angles are equal, all loads must also be equal. So with 100 kilograms here, we must have close to 100 kilograms on each of these. So you'll see there's 97 up there, and there's 98 up here. So it's pretty close to the 100 each side. Okay, so let's put that on the board. 120 degrees, 100% of the load. So it should be a bit of a caution happening there, because now whatever's here is also there. And it stands to reason that if we increase that beyond 120 degrees, the load on the anchor is going to be more than what's on here. So we're going to prove that as we go through. Okay, 150 degrees now. Now 150 degrees is very difficult to pick. You're going to need a smartphone or some protractor or something to establish that that's actually 150 degrees. It's a bit hard to use a rule of thumb. So 150 degrees up there. Now you'll see at 150 degrees I've got over 190 kilograms on each anchor, which is sort of what we were expecting. 100 kilograms here, 191, 191. So let's put that on the graph. 150, 190, let's call it 200. 200 is a nice even number. Now the issue comes here that this is inaccurate. I can't judge that easy, and the error here creates a big difference up there. So I'm going to make a slight change to this. I'm going to move this down one peg. Okay, so I'm going to go from 150 to 152 degrees. And we want to measure what happens on the load cells when I make that 2 degree change. So at the moment we're reading 190, 190. Okay, so we went from 150 to 152 degrees. We also went from 190 to 215 kilograms. So an increase of 2 degrees gave us a 25% increase in loading. That minute change. Now I can't see the difference between 150 and 152. I'm flat out seeing the difference between 150 and 160 visually on an anchor system. So that tiny little difference makes a big difference in loading up here. Okay, so the graph, when we graph this thing, actually I might put in a few other numbers. As a rough estimate, 160 is 300. 165 is 400. So you can see that that's a very steep ramp as we leave 120 degrees. So let's put a curve in here. It starts here at 50, it's way up there. Okay, so let's draw some assumptions in here. I'm going to start with the green zone. So the green zone is a good zone. And I'm going to say between 30 and 90 is a green zone, green for go. I'm going to say between 90 and 120 is a cautionary zone. You have to be very mindful that once you go over 90, you're starting to get more and more load on the anchor. Once you get to 120, whatever's on the load, whatever the load is, that's on each of those anchors. And once you go beyond 120, I'm going to paint that red. So we're going to paint that red because that's what we consider a fairly dangerous area. Now I'm not saying you can't rig stuff with that in there, because we do that quite often. If you look at high lines and things like that, and sometimes you do offsets that you've got quite a tight angle inside there. What I'm telling you is, once you get into this red zone, you've got to know the physics behind it. You've got to know some other ways of managing how to establish what those angles are and ultimately what the loads are. Okay, so our first rule of thumb I'm going to give you, first rule of thumb is keep the angle between 30 and 90 degrees. Okay, so we're back to 90 degrees. I just want to point out a few components that we've got here. We call this blue line, or in this case, this is our load line. Load line comes into a focal point, and from there we've got our anchor legs back to the anchor points, in this case through the load cells. I'm going to add this sling here to demonstrate what we call a projected load line. So if I pull that up tight, just imagine that this is the load line and it runs up and we project that through here, this imaginary line that we're putting in place, this Dyneema sling. So that's our projected load line, and you'll notice that the projected load line in this case bisects that angle, which means it splits it in two. Okay, so we've got 90-degree angle there. This one comes through the middle, so essentially we've got 45 on each side. Okay, and in that case we've got balanced load. I've got 69 kgs, 69 kgs. Now what I'm going to do is I'm going to radically shift this load sideways. So I'm going to shift it across sideways. We're going to see what effect that has on the loading. So I'm going to shift that across sideways. Let's look at where this projected load line ends up. Should end up somewhere there, so we've got a nice straight line. Now you'll see that the projected load line now is closer to this sling than it is to that. Now the effect up on the anchors is this one's gone down. This one went from 70 down to 58. This one here has gone from 70 up to 76. So any time when the projected load line doesn't bisect the angle, we're going to have different loads on each anchor. Okay, so I'm going to bring that back to the middle. So it's going to hang normal. Projected load line should be somewhere about there. So that should be a straight line. And these things should balance, 69, 69. Okay, so a second rule of thumb, the first rule of thumb was keep the angles between 30 and 90. The second rule of thumb is to keep this projected load line bisecting the angle. Now you might be looking at the chart thinking, what's the go with this little box down here? What's the go with this angle between 0 and 30? Well, I want to talk about that specifically. A lot of organisations have a system where they talk about anchors and they say there's an I, a Y and a T. Okay, so I would be these angles nice and tight, so down in here, and they say I stands for ideal. Y is what we've got here, so it's a Y shape, and Y stands for yes, so yes, you can use it. T is when they're really tight like that, and you're up in this angle, up in this area, and they suggest T stands for terrible. Well, I want to challenge the I want to challenge, and I'm going to put some cautionary notes about having angles nice and tight. Okay, so we're going to drop this load down, bring that back in. Okay, so I've dropped this angle back to close to 10 degrees. And if you look at 10 degrees, it looks pretty good. I've got 50.5 and 50. So 50-50, and that sort of matches up here. At 0 degrees, it's 50-50. It all sounds good. The problem comes, though, when I have a slight shift in the load. So I'm going to move that slightly, probably only 3 or 4 inches, or 70, 80, 100 millimetres. We're going to see what happens to that. So essentially, when I shift that there, I shift that projected load line back over closer to this one. It's just very difficult to see. Over there, I've gone from 50 back to 25, so I've halved the load on that one. And I've gone from 50 up to 72.5 there, with a very little shift in this. Okay, so I'm not saying you can't rig stuff down in that tight angle, but what I'm suggesting to you is you've got to be very cautious with it to ensure that our load doesn't move and that we balance the load evenly between these two strands, if it is that you're going to try and make a load sharing anchor. Okay, so we're back out to 60 degrees now, and I've put the projected load line in there. So just remember the 2 rules of thumb: keep the angles between 30 and 90, make sure the projected load line bisects that angle. Okay, I just want to make a couple of acknowledgements. The first one is this sheet over on the side here. I pinched this chart from Reed Thorne. I watched him present a chart in one of his courses where he had degrees and he had percent there, and he put this line in Didn't have the shaded section underneath, but he put the line in there. And I looked around the room and I saw a lot of people understood it. The penny dropped, so to speak. So yeah, I've pinched that off Reed. Thanks for that. A few other things. About 5 years ago, back in 08, 09, we bought some load cells. So we bought all these load cells to use in training. They had clunky rose joints on them, which were difficult to use and a bit cumbersome. So the first one we did was we pulled apart a Rock Exotica Omni block and we put the components either side of a load cell. So now we can run a rope through that. We can measure the actual magnitude of that resultant force through there, back through an indicator, which worked pretty well. The other thing we did was we married up an old laser pointer to the side of it so I can put a green dot that indicates the direction of that resultant force. So not only can I do magnitude of the force, I can do direction of the force with that. And it's a really good learning tool. About a year after that, I rang Rock Thompson up from Rock Exotica, told him what we were doing, and he sent me out some swivel beaner carabiners and some of the beckets from the pulleys. And a local machinist I got, Andrew Silmanovic, he made up the fittings to join them all together onto a load cell, so that's what you see there. The latest addition to the load cell group is this one. So Andrew machined up a few fittings for me to put an S-type load cell into a leg. So this represents a vortex leg or any other type of high directional leg. And we can measure the compressive force down there, so it just gives a negative indication on the indicator of force. So we can set this up inside our black frame here. We can put different angles back to the frame, different angles to the load, and we can demonstrate what those minor changes in there give as a result in force down the pole and back to the guys and anchors. Okay, so that's about all we got time for today. Thanks for watching.